My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Adda, and the YouTube channel, Pretam Kumar Das, and Facebook page, School of Astrophysics and Astronomy. So I'd like to welcome you all to our International Physics webinar. So good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. So today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and Department of Physics and Astronomy, Dartmouth College, USA. And today it's our 170th International Physics webinar. So today we have with us here today Dr. Ryan Hickox, Professor at Department of Physics and Astronomy, Dartmouth College, USA, and he has already connected with us. So I'd like to welcome our speaker, sir. Good evening and good morning to your part, and thanks for accepting our invitation, sir. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. So for those who are new, I'd like to inform you all that we have divided our webinar into three parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion session. In that time anybody can join with us. So I think you have already come to know the title of this today's International Physics webinar, and title is the Supermassive Black Holes and the Growth of Galaxies. Very interesting topics. I think you will like it. So our speaker is Dr. Ryan Hickox, Professor, Department of Physics and Astronomy, Dartmouth College, USA. So Professor Hickox is an observational astrophysicist with primary interest in supermassive black holes and the evolution of galaxies. He has a BSc in physics from Yale University and a PhD in astronomy from the Harvard University. He held postdoctoral fellowship at the Smithsonian Astrophysical Observatory at Durham University in UK and joined Dartmouth College in December 2011. His research has been funded by NASA, the National Science Foundation, including Career Awards and Alfred P. Solon Research Fellowship. Professor Hickox also served as the House Professor for West House. You can see his educational and experience. So this is his research interest. So active galactic nuclei, galaxy evolution, large-scale structure of the universe, the cosmic X-ray background, X-ray binary stars, work in progress, connection between supermassive black holes growth and star formation in the galaxies, and Herschel and Chandra data, spectral energy distribution, selection and clustering of obscure quasars with SDSS, WISE, SALT and a new star, X-ray stacking analysis, and Chandra and a new star. This is his selected publication and Inspire Hep ID. This is Google Scholar ID. You can see his citation is more than 10,000, and this is his ResearchGate ID. His research point is 42.39. So thanks all of your patience. Now it's time to go to our speaker, sir. I'd like to welcome you again, and it's your time, sir. You can start your session, sir.
All right. Thank you. Just a second. Let me share screen here. Just a second. Share screen. Share screen. Entire screen. Share. What did you do? Wrong one. Sorry. 1 second. Here we are. All right. Is that coming through okay?
Yes, sir. It's okay.
Great. Okay. Well, thank you very much for having me here. It was very.
Yeah, it's a pleasure, sir.
Okay. Is that working?
Yeah, it's working.
Okay. Perfect. Yeah, it was a great privilege to be invited to come and talk to you all. And so, again, I'm Ryan Hickox from Dartmouth College in New Hampshire in the United States. And my research is broadly speaking on supermassive black holes and the growth of galaxies. And so today I'll give you sort of a general tour of what we know about the growth of supermassive black holes and how they're connected to the evolution of structures in the universe. And again, I would love to answer any questions if you have some when we get to the end. So first off, just to highlight Dartmouth College, some of you around the world may not know about Dartmouth. So Dartmouth is one of the 8 Ivy League universities in the United States, which are among the oldest and most prestigious, as it were, institutions here. And so this is a picture of our nice location in the mountains here in New Hampshire in the US. And I'm very fortunate to have an active research group here that involves PhD students, postdocs, and undergrads. And so I'll show some work that was done by various members of this group as we go along, although in this particular talk, I'm going to give more of a general overview of the field. I would, however, like to highlight Tanima Anana, who's a postdoc in our group, who is originally from Bangladesh. She did her PhD at Yale and has been a postdoc with us for the last couple of years. And she actually was one of the 10 young scientists to watch for in Science News this year. So she's been, her work has been highlighted around the world, and she's really an extremely promising scientist. And so I will show you very briefly an example of the sort of thing that she works on. But we're very particularly excited to have her in our research group here. There are also a large number of Dartmouth alumni. For those of you who, of our group, for those of you who are active in the field, you may recognize some of these people, but they are active at a range of institutions from Harvard to Caltech to Arizona and other places. And so we're very proud to have put some excellent scientists out into the world. Okay, so we're going to talk about supermassive black holes. And the best place to start when talking about them is, of course, the one that's most nearby. That's the center of our Milky Way galaxy. So this is a visible light image of the center of the Milky Way. There's a lot of dust and gas in between us and the center of our galaxy. But if we go and look at this galaxy in particular in infrared light with very high resolution telescopes, like we have with the Keck telescopes in Hawaii using this advanced laser guide star adaptive optics system, if we go and take an infrared image of the very center of our galaxy, we can see the positions of a lot of stars right down near the center. And you can make a movie of how those stars move now over time, over many years. And this is these observations are really amazing because the scales are tiny. Less than 0.1 arc seconds, we are able to locate the positions of these stars, which is much, much better than you would typically be able to do from the ground using just a regular ground-based telescope. So this amazing adaptive optics system really gives us this capability. And if we turn this on and watch it over time, what scientists have been able to do is actually track the motions of stars around the center of the galaxy over decades. And if you look at the motions of these stars, you can see that they all follow around one particular point. And that point actually doesn't have a huge amount of infrared or near-infrared emission coming from it. It's quite dark, but if you work out its mass, in order to hold these stars in those orbits going around so quickly, it must have a mass of around 4 million times the mass of the sun. And so this is what we believe to be the supermassive black hole at the center of our galaxy. And as many of you are familiar, this is an award for which, this is a discovery for which Andrea Ghez and Reinhard Genzel were recently awarded the Nobel Prize in physics. So so we have this huge thing, this enormous black hole at the center of our galaxy. I think probably everybody watching this is familiar with what a black hole is. It's an object that's so dense or has such strong gravity the light cannot escape from it, and so it has an event horizon around it where there's effectively an infinite warping of space-time. This thing has a huge mass, a mass of 4 million times the mass of the sun. And so a kind of immediate question is, where did that mass come from? How did all this material get down into this black hole in the center of the galaxy? Now we think we know the answer. The answer to that is actually accretion of material onto the black hole, releases gravitational energy and produces radiation. And we can see that using an X-ray image of the center of our galaxy. This is the Chandra X-ray Observatory took a high-resolution X-ray image. And if we watch a movie of this, you can see that there's actually a neutron star that's emitting a lot of radiation near the center of the galaxy. But if you watch over time, there will be a flare, boom, from the center of the galaxy that's produced by accretion onto the central supermassive black hole. And so the idea is you have a flow of material that's being attracted by the black hole mass. It has some viscosity, it loses gravitational potential energy, and as it falls into the black hole, it produces a blast of radiation. In the more general sense, our black hole is actually relatively quiet. It's not accreting very fast. It's not producing a huge amount of radiation at the moment, although we'll talk about what happened in the past in a little bit. But in general, this accretion process can be described by something called an active galactic nucleus. And basically, we think that the center of an active galactic nucleus, or AGN, looks like this. You have a disk of material that has some angular momentum that is driven down towards the black hole and then goes in orbit around the black hole. And in the process of accreting, it loses some angular momentum, loses some energy and by radiation, and falls into the black hole. And it turns out that this process is extremely efficient at producing radiation. And so if you theoretically work out what the luminosity is for a particular mass accretion rate onto a black hole, it turns out it's about proportional to the accretion rate of rest mass. That's m dot c squared here. And the efficiency of this, the conversion from this rest mass to luminosity, is amazingly high for a accreting supermassive black hole. It's about 0.1 or 10%. Whereas if you think about, for example, the PP chain, the way that fusion happens in the sun, that same efficiency is about 0.7%. So this is an enormously effective way of producing radiation. And in fact, it allows these accreting black holes to be among the most luminous objects in the universe that we can see to the very edge of the observable universe. So most of the things that we look at produce their energy in the form of this radiation. Occasionally, we see ones also that produce very powerful mechanical outflows in the form of relativistic jets, materials connected most likely to magnetic fields that are accelerated at high speeds near the speed of light above and below the accretion disk. And we'll see some examples of some of those later on. Let me turn down the sound here a little bit. I don't know if the sound is coming through, but this process can produce a gigantic luminosity. This is an artist's impression of a very distant quasar that has an enormous luminosity. And if you place something this luminous, there's a black hole down in the middle. In the center of a galaxy, it profoundly changes what the galaxy looks like. So most galaxies would look something like this. This is a nearby galaxy called Messier 81. But if you have a growing black hole in it, it instead looks something like this. The light's completely dominated by the radiation produced by the growing black hole, and you get something called a quasar, which is a very luminous active galactic nucleus that can outshine the light from the hundreds of billions of stars in the galaxy put together. The total power of a powerful quasar, and this is arcane units of ergs per second that we use in astronomy, so I apologize to my physics colleagues. The equivalent number is about 10 to the 40 watts. A gigantic amount of power is produced by these powerful quasars. It actually can be kind of hard to visualize how much power that is. So I have a nice little sort of semantic or a heuristic that you can use for that. You can ask, what is there something of which produces a lot of power and then something of which there are many on the Earth? So a hydrogen bomb, the largest hydrogen bomb ever produced, produces about 10 to the 24 ergs of energy. And if you ask how many grains of sand are on the surface of the Earth, there's about 10 to the 22 grains of sand on the surface of the Earth. So if you multiply these two together, you get that the power of a quasar is equivalent to 10 hydrogen bombs going off per second for every grain of sand on the surface of the Earth, which is truly amazing. So it gives you a sense of really how powerful these objects are. And of course, as someone who gets to study this for a living, this is an exciting thing for me to think about. But we'll talk in a little bit about actually the profound effect that energy can have on the galaxy that the quasar sits in. Okay, one other important thing to know about black holes in galaxies is that they are the kinds of black holes that we see in galaxies around us. So we see one in our Milky Way galaxy. We also see them in many other galaxies, and I'll show you a really well-known example here in just a minute. Typically, the mass of a black hole is related to the mass of the galaxy in which it resides. So bigger galaxies, especially ones with bigger bulges, have larger black holes in them. So a big elliptical galaxy might have a billion solar mass black hole, whereas a spiral galaxy like the Milky Way might have one that's more like 1,000,000 solar masses. But also, an important number to keep in mind is that these galaxies themselves reside in huge halos of dark matter, which is the material that provides a sort of scaffolding for structure formation in the universe. And so they reside in these dark matter halos. And the typical dark matter halo for, say, a very massive galaxy will be around 10 to the 13 times the mass of the sun. Now, an interesting feature, I mentioned that this radiation that's produced by the black hole can strongly influence what's going on in the galaxy. If you just take all the gas in a 10 to the 13 solar mass halo and you work out what is the total thermal energy, just the KT energy associated with that, it's about 10 to the 61 ergs. If you work out the total accretion energy, that's just that epsilon factor that I talked about before, times the mass of the black hole c squared. In other words, how much radiation was produced over the course of this black hole growing over its whole life. It's about 2 times 10 to the 62 ergs. So there's 20 times as much energy released by the black hole as there is binding all the gas in this huge halo, which means that the growth of a black hole can have a really profound influence on its surroundings. So that's kind of our general motivation. What I want to do now for most of the rest of this talk is just take you on a tour of what we know about growing black holes and how they might be connected to their structures that they live in. And so black holes, they have phenomena that manifest on a large number of scales. One you can think about, the smallest scales are around parsecs. This is, parsec is a few light years. So this is the scale right down at the center where the accretion is going on. We'll then move on to talking about what we see on scales of galaxies, or thousands of parsecs. And then finally, we'll talk about these big dark matter halos, which are on scales of millions of parsecs, and ultimately up to the very large scale structures that we see in the cosmic web. So I'm going to kind of step through each one of those as we go along. So let's start off with parsecs. What happens right down in the middle around a growing black hole? Well, this is a sort of complex diagram that was produced by Cristina Ramos-Almeida and Claudia Ricci for a nice review article of theirs, that gives you sort of a multi-scale view of what we think the general structure around a black hole is. And you'll notice this is in log space on this scale axis. So there's many, many orders of magnitude involved in terms of the relative scales. So you have the black hole down here in the middle. You have this accretion disk that we showed you before. You have some fast-moving material we call the broadline region clouds, and then you have some sort of dusty material farther out. And all connected to this, we have some outflows. And so I'm going to take you on a tour of a few different pieces of this. So the first is actually the black hole itself. For many years, we've kind of speculated about what the region right around a black hole would look like, but we hadn't actually been able to take a direct picture of one. That is until a few years ago. This is this tiny scale, by the way, microparsecs. The scale of a black hole is on the order of astronomical units. So it's something that's the size of the solar system. We were now actually able to take an image of that, and this is a great movie from the Event Horizon Telescope. I'm sure you've all seen this, of the nearby galaxy Messier 87. We're going to talk about M87 later. This was released in 2019, so you're all familiar with this. This is zooming in close and closer and closer to the center of the galaxy with a microwave observatory until we were able to actually take this image of the dark spot corresponding to approximately the event horizon of this black hole. And I'm guessing most people on this call have seen this image before. This, I think, was the most downloaded image in the history of the internet at the time that it was produced. So this is, in this very nearby galaxy with a really big black hole, this black hole weighs about 6 billion times the mass of the sun, we're actually able to work to see the structure and the flow of material coming onto it. We can't see that for other galaxies, but we can infer the relative scales by looking at the properties, and especially the time evolution of some of the radiation that's produced. So we've begun to look at this here. I could go through lots of details of all this stuff, but one of the most interesting ones, I think, to zoom out a little bit is to look at this dust. The region now on scales of, say, a parsec to tens of parsecs that are associated with the accretion flow of material onto the black hole. Simulations of this material show an amazingly complex and dynamic structure. So this is a lovely simulation from several years ago by Keiichi Wada and collaborators. This is now zooming around, showing the dust coming into the black hole. This accretion, the accretion's going around along this axis here. So dust forms there. The black hole then accretes and produces some radiation, and that in turn produces these cones of dust that are illuminated and blown out above and below the growing black hole. So this is what the hydrodynamical simulations would tell you for what potentially this structure looks like. Again, however, until very recently, we actually haven't had the capability to measure this directly. But now, using new observational capabilities, we can, and this is in particular using the MIDI interferometer on the very large telescope interferometer. So this is these 4 telescopes in Chile. Their telescopes are combined together to do interferometry in the mid-infrared. They look at the Circinus galaxy. This is one of our nearest black galaxies that has a rapidly growing black hole in it. And so this measurement, what you actually get, for those of you who are familiar with interferometry, what you actually get is correlated flux or visibilities from interferometry, which can be hard to interpret. But this paper does a nice job comparing what they observe to models. And it looks like the best models that you can have to actually explain the data look very much like that simulation, with a sort of disk of dust along the axis of the black hole, and then these dusty regions above and below caused by radiation blowing dust out. And so we're starting now, and as we get bigger telescopes and more powerful interferometry, we'll make better and better views of what the actual central region around the growing black hole looks like. And again, these units, for those of you who do astronomy, these units are milliarc seconds. So you're getting structures on very small, very, very small scales, corresponding to the parsec scale structures in a galaxy that's many millions of parsecs away. Okay, so there's many other bits of this that I could talk about, and we study all aspects of the growing black holes, but one other important one that will become especially important later on is this outflow. So I mentioned that the black hole, the accretion energy of the black hole is large, and so it can produce, it can strongly impact the gas in the galaxy and produce a powerful outflow. It turns out that when we look in AGN for these outflows, we see them all over the place. Normally, in a couple different ways. One is that we can actually see fast-moving gas. So we see this by the Doppler effect, the blue shift and red shift of absorption or emission lines. And so one thing we see, for example, on very small scales is X-ray emission, very highly ionized gas that's moving near the speed of light. So that's stuff that's being accelerated very rapidly by this large radiation. Out on larger scales, you can see molecular and atomic gas. This is now gas that's a bit cooler, that's moving at thousands of kilometers per second, or say up to 1,000 kilometers per second or so. So enough to really get blasted out of the center of the galaxy. And then on very large scales, we actually see outflows in molecular and also ionized gas, where that emission, or those outflows that started on the very small scale get spread out to larger scales and slow down, but also reach much larger sizes. And so no matter where we look, and piecing together this picture can actually be pretty tricky, but no matter where we look, we always see evidence that the black hole is doing something in terms of impacting the gas around it. And as we'll see in a little bit, that actually has an impact on how potentially galaxies form stars. Okay, so let's talk about galaxies. Let's move out now from that small scale out to the larger scales of thousands of parsecs that correspond to galaxies. I love this movie. Whenever I talk about galaxies, I always show this movie. This is a lovely visualization of the nearby universe taken from the Sloan Digital Sky Survey. So there were distances and images measured for millions of galaxies by Sloan. And this is a sort of visualization of what it would look like to fly through that volume. So I always think this is just amazing to see. This is what the universe really looks like if you were traveling, if you were able to travel through it way faster than the speed of light. and not have any of those, time dilation effects or anything. And so looking at, you can see a couple things here. One thing is that you notice that there are lots of different kinds of galaxies. There are some that are blue and sort of disky. There are other ones that are sort of red and shaped more like a rugby ball. And that they're not distributed randomly in space. They actually they make up these structures. So you see them along filaments. You also see them in big groups and clusters. And that, as we'll see later, is actually due to the fact that these galaxies form inside of big dark matter structures. So this is where, generally when we look out at the universe, we see all these galaxies that are primarily made of stars. And so they formed their stars somehow over the history of the universe. Only a fraction of them at any given time actually have a growing black hole. And so one of the main things that we do in my line of research is to try to understand which galaxies have growing black holes in them and connect that to various properties of the galaxies. So how do we actually identify an active galactic nucleus? Most galaxies don't have a strong AGN in them. How do we actually go about doing that? Well, we can use a number of different methods. And in particular, my group focuses a lot on methods using the X-rays, the infrared, and the ultraviolet and optical. And so this is a nice little movie from a review article that David Alexander and I wrote a few years ago, highlighting what happens to the overall light from a galaxy when you put a growing black hole in there. So this is a spectrum showing the brightness of the galaxy as a function of wavelength or frequency. And these are the different wave bands that you might observe in the mid-infrared, the optical, the soft X-rays, and the hard X-rays. And these are kind of a simulated image of what a galaxy would look like. So this is with a very weak AGN. You see that the light is mostly dominated by stars, and in the X-rays you get some hot gas and some little neutron stars and black holes in the galaxy. As you crank up the power of a growing black hole, though, you start to see that the light gets dominated by the black hole, either by the dusty emission from that dusty torus around the black hole that comes out in the mid-infrared, or also X-ray emission coming from in quite close to the black hole, and visible and ultraviolet emission coming from the disk of material. And so all of these have signatures that make it very straightforward to identify a black hole. One problem happens that if you actually then put some gas in front of this growing black hole and dust in front of it, what it'll do is actually absorb most of the optical and soft X-ray features. So this shows what happens when you include this absorption. But the X-rays, especially the higher energy X-rays, and the infrared signatures still remain there. And so a lot of our work focuses on these because they're less susceptible to the effects of this obscuration. And so in particular, X-rays, my initial training is as an X-ray astronomer, and that's where a lot of my focus has been over the years. What we can do is take telescopes like the Chandra X-ray Observatory and observe a big patch of sky and find lots and lots of little X-ray sources, each of which corresponds to a galaxy. And this gives us a big census of growing black holes. And so this is an image of a very large field called the X Booties field. And the most recent analysis of this was done by Alberto Massini in 2020. This has thousands of AGN and about 7,000 of them in this 9 square degree field on the sky. There are other fields that are, somewhat smaller that have been observed more deeply. Here's another example of one, the Cosmos field. This is a paper by Francesca Trevano, who's also, both of them are alumni of our group here at Dartmouth. And then if we zoom in on the very smallest scales, you can get to really, really deep X-ray observations. This is the Chandra Deep Field South, which is a tiny patch of sky that was observed really deep. And in every case, each one of these little X-ray sources pretty much corresponds to a growing black hole in a galaxy. So we can use this and other techniques like what the galaxy looks like in the infrared part of the spectrum to tell which galaxies have growing black holes in them. And so you can end up making a map. So this is a three-dimensional rendering of the three-dimensional distribution of galaxies in that particular 9 square degree field, the one that I showed first. So the green points are all the galaxies, and the purple points here are the ones that have these X-ray bright AGN in them. So one thing you'll notice right away is that the black holes, growing black holes, basically follow the same kind of large-scale structures. And I'll pause this for a second because it gives you vertigo if you look at it for too long. that the growing black holes follow the same kinds of large-scale structures as the galaxies do, but most galaxies don't have a growing black hole in them. It's only a small fraction of them. So we can do more than this. We can actually go and try to work out what are the properties of the galaxies that actually host these growing black holes. And so what's the connection between the growth of galaxies and the growth of black holes? So as a quick aside, for those who are not familiar with the various properties of galaxies, I just want to do a quick aside about galaxies and star formation. So I showed you that distribution of galaxies in the universe before, where we were flying through. And we pointed out that galaxies are not all the same. They have different properties. And one of the ways in which we draw or we point out these properties is by looking at two properties of a galaxy: how luminous it is, which is related to how many stars it has, and how red it is, which is related to how old those stars are. So if you form a lot of stars all at once, the hot, young, massive stars will dominate the light. And since they're hot, that light will be blue. Over time, those hot, young, massive stars, they blow up first. They become supernovae, and they die and leave only the cooler, less massive stars, which have redder colors. And so how blue a galaxy is directly related to how much star formation you have. If you have lots of blue light from young stars, then you have a lot of star formation. So typically also we know that galaxies that are blue also tend to have spiral morphologies, sort of like the Milky Way. They look like disks, whereas red galaxies tend to be more shaped like a rugby ball and have less structure and be more spherically symmetric. So if we can find out which kind of galaxies growing black holes live in, then that'll give you a hint as to maybe what some of the connections are between black holes and galaxies. So we've done this. Way back in 2009, we did one of the first papers that looked at a comparison of this using different selection techniques for growing black holes. And what we found is this is, again, that distribution in luminosity and color for black holes selected in the X-rays and one selected in the infrared. And what we found is that mostly, except for the very reddest galaxies, the black holes, growing black holes, are basically found everywhere. They're maybe a little more likely to be in the more luminous galaxies, and they're not in the absolute reddest ones. But otherwise, this whole sort of area where they're forming stars, these growing black holes are all over the place. It's also been shown that if you look at the morphology of these galaxies, they're kind of all over the place. A lot of them are disks, but a good fraction of them are more of these spheroids, and some of them are, mergers or other kind of complicated structures. So basically, growing black holes are everywhere. They're found in all types of galaxies. We showed this in 2009. We also show, by the way, that radio bright sources, and I'll get to this a little bit later on, the ones that are radio bright, these are ones that primarily the radio comes from synchrotron emission from one of those relativistic jets. Those are primarily found in the very red galaxies, the ones that are not forming stars anymore, and typically the most massive ones, the ones that are most luminous. So we did this in 2009. In 2014, we expanded it out into looking at multiple fields that allowed us to probe different parts of cosmic time. So we could look quite nearby to us using that Sloan survey that I showed you before. And we could also look at galaxies that were very far away using data from something called the Deep 2 survey, where now we're observing galaxies when the universe was only half its current age, because the light takes the time to reach us. And so, we're seeing how these things change over cosmic time. And generally, the key point, this is a nice paper by Andy Golding and collaborators, the key point is that nothing really changes. This story is pretty consistent across all of cosmic time. So this kind of complicates things a little bit, because I told you that the mass of a black hole is connected to the mass of the galaxy, and that it's the gas supply in the galaxy that ultimately accretes onto the black hole. So you might expect that galaxies and black holes will grow together. However, if we look at this, doesn't seem to be really a very clear match between which galaxies are, there's not really a very clear trend about the properties of the galaxies and which ones are growing. It seems like they black holes kind of randomly populate galaxies. So is it just totally random? Are these two processes completely uncoupled? Or is there something else going on? And so the way we looked at this was to say, wait a second. Yeah, it's true that at any given time, a growing black hole may be found in any type of galaxy. But what if we average this over properties of galaxies? And in particular, what if we find a way to measure the rate at which a galaxy is forming stars and average up the luminosity of the black hole? That will give you an average m dot based on that equation that I showed you before. And so that'll tell you roughly how fast the black holes are growing for galaxies of different star formation rates. So you can make a simple prediction, which is that if the galaxies and black holes grow together, then the observed star formation rate, or in other words, in this particular case, we're using the far infrared luminosity, but it can be scaled to the star formation rate, should be proportional to the average luminosity of black holes averaged over the whole galaxy population. So my student Chen-Ting Chen did this as part of his thesis a while ago, and some other people have done similar things. And we showed in a paper now way back in 2014 that indeed, actually, this seems to work, that there's a nice, clear relationship between these two things. So that tells us, okay, maybe actually in general, galaxies and black holes do grow together, even if what we see is sort of a stochastic process. We can even do this in a more general sense by trying to model the growth of all the black holes we see and get a picture of what is the integrated rate of black hole growth over cosmic time. So this is something that Tanima Anana, who I introduced before, has done for her PhD thesis. She produced a wonderful model of the overall growth of black holes, and this is the one sort of long equation I'm going to give you in this talk. The growth of black holes at some redshift, that is some age in the universe, is just the integral of all of the luminosities of all the black holes in that redshift range. That's what these various things correspond to, with a correction factor corresponding to the radiative efficiency. She calls it eta here. We called it epsilon before, but it's the same thing. And so if you do something like this, you can then get an estimate for what the black hole accretion rate is as a function of cosmic time. And this is an older prescription, but I've showed this one because it sits nicely on top of also what some measurements are for star formation. And the interesting thing is that you can do the same measurements for star formation. I won't go into how you do that. But over cosmic time, black hole accretion and star formation basically track each other very well. So if you look back in time corresponding to earlier in the universe, more expansion, so a higher redshift in the universe. If you go back about to redshift between 1 and 2, which corresponds to an age of the universe of about 7 billion years or so, that's when the peak of black hole growth in the universe and also the peak of star formation is highest. So this is the rate of star formation or black hole growth per cubic megaparsec, that is per cubic volume in the universe as a function of time. And so this is kind of neat. What this is telling us is indeed the black holes in the galaxies are on average growing together when aggregated over the entire universe. And Tanima's work is, I think, among the most robust of any of these estimates that we have now. It's an improvement on this one. Okay, so that's the story. AGN are found in all types of galaxies. On average, black hole growth broadly follows star formation and or the mass of a galaxy. But instantaneously, AGN can actually have a very broad range in what their luminosities are, and they're sort of a stochastic process. So they're not light bulbs. They don't just turn on and grow and then turn off again. It's something more complicated. And what our group has been sort of on the forefront of over the last number of years is to try to understand this in terms of what we call flickering. So black holes do appear to grow roughly along with their host galaxies over cosmic time, but on short time scales, say time scales of thousands, say hundreds even to up to 1 million years, the black hole accretion rates can change like crazy. They actually flicker on and off. And so this is a simulation from Greg Novak et al. This is an older one now, showing the Eddington ratio, which is related to the black hole accretion rate over cosmic time. And over the course of millions of years, this can fluctuate by 7 orders of magnitude. Now, in this time, you actually don't expect the galaxy to change very much. The typical growth times of galaxies are sort of 100 million years or so. But in that time, the black hole will have been flickering like crazy. Sometimes it's super, super bright. Other times it's totally off, more like the black hole in our own Milky Way. So that's the way we need to think now about the growth of black holes and galaxies. And I think our field has moved towards this understanding that we need to think about it as like an ensemble statistical problem. So that's how we approach this in the work that we do now. Okay, so that's the way we're looking at it. A lot of those details are still to be worked out. But the last part I want to focus on are the large-scale structures. What happens when we move out to the biggest scales in the universe? And so to start with that, I wanted to start with a simulation just showing the growth of structure in the universe. And so this is an older simulation from called the Millennium simulation that really kicked off a lot of this field. So this is showing, you start off in the early universe, there's very little structure. This is redshift of 20, so corresponding when the universe was only 100 million years old or so, even less perhaps. And as the universe starts off with very little structure, but the overdense regions grow under gravity through gravitational collapse. And so you end up collapsing, the dense regions become denser, the less regions have less gravity, they become more diffuse, and you end up collapsing into this cosmic web of structures, inside of which these halos of dark matter that we talked about before, that's where they form. So this is how the galaxy formation process proceeds. And if you zoom through this dark matter, this is a simulation actually that was done just with dark matter. Dark matter dominates the mass in the universe and doesn't experience the forces that baryonic matter, the normal gas, does. You see these dark matter halos. Inside these dark matter halos are actually where galaxies form. So here's another simulation now, including the gas, showing how normal matter, hydrogen and helium, for example, collapses down into galaxies, and they are forming, the galaxies are actually forming at the center of these dark matter halos. This is the picture we have for how galaxies form over the history of the universe. Okay. So what you can do is take observations, and you can actually map what the relationship is between the stellar mass of a galaxy and the mass of its dark matter halo. And you think immediately maybe this is just linear. A bigger dark matter halo has a correspondingly larger galaxy. But it turns out it's a little more complicated than that. There's actually this structure where as you increase in dark matter halo mass, you get more and more efficient at forming stars until you reach a certain mass, and then you become less and less efficient. And so right at this kink here is actually where the black hole, the ratio to a galaxy mass to black hole mass is the highest. And interestingly, that's exactly where the Milky Way lives. So we are in one of these halos that are most efficient at forming stars. Now, why is this? What's going on here? Well, it turns out the black holes have a lot to do with it. So this is now turning that plot on its side. This is star formation efficiency. We know there's a lot of processes that go on. So on small scales, it's hard to form galaxies just because actually it's hard to get the gas to cool at all to form into stars. Once you get up to somewhat larger scales, you have heating from stars and supernovae, exploding stars, that blow out gas, and they will therefore not form so easily into stars. When you get to the mass of around 10 to a trillion solar masses, which is about the halo mass of our Milky Way, then you get to the point where actually we're pretty good at holding on to, there's enough gravity to hold on to the gas, and the processes that would drive stuff out are not all that effective. But as you get to higher masses, then you start to find processes where the black holes start to get pretty big, and they get really good at driving winds. And at the very largest scales, actually, the gas just stays hot because of the way that it was formed in from the cosmic web. It gets shock heated on its way in. And so these processes, and in particular the impact of the black holes on the massive end, are really important for understanding how structures in the universe form. This is another simulation showing the growth of black holes. This is the illustrious TNG simulation. And this shows the growth of stars on this side, and this is the gas in the galaxies, or in these systems on that side. And you can actually see the impact of the black holes in this simulation. The black holes are blowing huge bubbles via the release of all that energy that we talked about before. So this is the theoretical picture. The question is this really happening? So where do the quasars live? These quasars are the most powerful growing black holes that we know of. In what kind of dark matter halos do they reside, and does it actually fit in with this picture? This is one of the things that our group is interested in studying. And so people have looked at this from many different angles, but our group has used a relatively new technique, which takes the cosmic microwave background, which is the echo of light from the very early universe, and uses the gravitational lensing of that light by structures between us and the microwave background to work out the masses of the structures that quasars live in. And so this is a nice simulation showing, this is what the background would look like without any structures in front. And by the way, this is highly exaggerated. But then if you put some massive structures in, it produces some features that can be easily determined from the decomposition of the image. And so what groups have done through various cosmic microwave background experiments is have actually done this to produce a map of the amount of lensing of the CMB between the very early universe when that light was emitted and when it reaches the Earth. And so the Planck collaboration, for example, produced a lensing map that looks like this. This shows us the integrated structure along our line of sight. So you can use this now, actually, amazingly, to figure out how big the structures are that quasars live in. Because if quasars are mostly in low density regions, then they'll mostly be found in these parts with not very much lensing because there's not a lot of structure there. Whereas they're in high density regions, that is massive halos, they'll be found in the denser ones. And so I'll spare you the details, but this is a work that's been done by a number of people. And what you can do is just cross-correlate the density of quasars on the sky with the lensing convergence that you see from those maps. And this is a nice figure from Jim Geach showing that low-density regions with not very many quasars have no or very little lensing convergence, whereas if they have a lot of quasars, they have a large lensing convergence. And you can more formally do a cross-correlation of these two things to work out the angular correlation between the lensing maps and the positions of quasars. And so what has been shown from doing this, and I'll spare you all of the details, this is a nice paper by Jim Geach from a couple of years ago, is that quasars are found typically in halos of around a few times 10 to the 12 solar masses, maybe up to 10 to the 13 solar masses, with maybe some trend with luminosity. This is actually a luminosity on this axis. The more luminous ones are in somewhat bigger halos. And so this tells us where these quasars live. And indeed, if we go back and put it on this diagram, the quasars are found right here, just above the mass of the Milky Way, and just in that part of this diagram where the star formation starts to become less efficient. So it's consistent with this picture that the growing black holes have some impact on the formation of these large-scale structures. Cool. So lastly, I wanted to just focus on what happens in these most massive halos here, because this is where we can kind of see some of the most interesting stuff going on. And I'll take you back to M87. This is that galaxy we zoomed in on before that has the enormous black hole that's been imaged by the Event Horizon Telescope. Messier 87 lives inside a big cluster of galaxies called the Virgo cluster that has an enormous dark matter halo. And if you take an X-ray image of this whole thing with the ROSAT observatory, you get this huge cloud of very hot gas that's embedded inside this big halo. But if you zoom in on this, well, so one thing to point out, if you look at this, is just from this X-ray image, you can show that the cooling time in the cluster center is really short. Millions of years, not tens or hundreds of millions of years. Or at least it's less than billions of years, which is what you would expect the overall evolution time of this structure to be. So why isn't the central galaxy full of cool gas and star formation? It's not. We saw a picture of it before. It's one of those dead elliptical galaxies. Well, we can find this by zooming in with the Chandra Observatory. So here's a visible light image, and this is an X-ray image with Chandra. And what Chandra shows us is there's all this amazing structure. This is the jet produced by the growing black hole that we talked about before. But then there are buoyant bubbles that we see around this, and also shocks produced by energy that's released via that jet. And so what's going on here is that the growing black hole is injecting this energy, in this case, probably more in the form of a relativistic jet than radiation, and that's profoundly impacting the gas in the system, blowing these big bubbles, producing these shocks, and all of this can ultimately heat up the gas in the system. Virgo is one of the, and M87 is a nearby example. This is one that we can study really well because it's so nearby, but nowhere close to the most extreme example. Oh, by the way, sorry, I had to just show this animation. This is a little animation showing of what we think is going on, that the black hole occasionally outbursts, and when it does outburst, it blows these big bubbles in the surrounding hot gas. This is a more extreme example, MSO 735, where this is the X-ray image, again showing these big bubbles, and this is the radio image showing the jets from the black hole. But now this isn't on an enormous scale. This is hundreds of kiloparsecs, way bigger than a galaxy. And so you can work out what the amount of energy it took to actually just do work, just PDV for anyone who's had basic thermodynamics, the amount of work that it takes to inflate this enormous bubble in this X-ray gas. And it's gigantic. So you can basically relate that then to how much mechanical energy you think is being produced by these radio jets, and also to how much energy would be needed to actually keep this system hot so that the gas didn't cool. So people have done this. They've looked at the cavity power, that is the total amount of power here that's taken to inflate these big bubbles, and what the cooling luminosity is. In other words, how fast is it cooling? How much energy would you need to sort of offset these two things? And they've done this for a large number of different systems. And amazingly, when you do it, they basically lie right along this line. So this is telling you that these black holes are actually regulating the baryons on the universe on really big scales, the scales of whole galaxy clusters. They have the structures they do, they have the temperatures and the gas content they do, because of these little black holes that, remember, they have a lot of mass, but they're only a tiny fraction of the mass of the system and only about the size of the solar system. They are regulating the gas on the universe on scales much, much larger than that. Cool. So there's a lot more to talk about here. This is just a very, very whirlwind view of this whole field. The last couple of things I wanted to mention. One is, let's go back to our Milky Way. What about our Milky Way? Well, we talked about how black holes flicker over time. And indeed, there's evidence of that happening in our Milky Way galaxy. So the Fermi Gamma Ray Observatory and the E Rosita X-ray Observatory have observed these gigantic bubbles in our Milky Way galaxy that were almost certainly inflated by a black hole episode some tens of millions of years ago. And this was released this year, actually, by the E Rosita collaboration. So our black hole actually does this fairly often, just, it's not going off right now. And that actually has really interesting implications, for example, on where you could live in our galaxy. There may actually be regions close in that planets would become uninhabitable because of the fact that they would be blasted so often by the radiation from this growing black hole. So this has some implications even on the habitability of galaxies. So finally, before I'm done here, I want to look towards the future. Many of the advances that we've made in understanding black holes come from new observatories. And one thing that I showed you is many of these high-resolution X-ray images that are good for identifying black holes and good for seeing the structures that they produce. So for example, this is a high-resolution X-ray image made with the Chandra Observatory. In the future, we would love to have even more high-resolution images. And so one of the, some of you may have heard of the Astro 2020 Decadal Survey, which is a big effort going on right now to determine the priorities for astronomy in the US over the next decade. And I'm engaged, or have been engaged, with something called the Lynx X-ray Observatory that would be designed to take images like this, that would allow us to identify the earliest growing black holes, very, very faint, small black holes in the very early universe. And there's a lot of other interesting science goals with Lynx. I will not go through all of these in the interest of time, but just to point out, if anybody's interested, if you go to hiddencosmos.org or Links Observatory, you can find out lots of the science details of that. We're going to find out about the decadal survey probably in the next month or two, and so it would be great to hopefully this will get prioritized, and links may be a reality quite soon. Okay, so I will stop there and just point out that black holes are an integral part of the evolution of the universe, and I'll give you one example of many of how the future of discovery is bright. So I will stop there, and I will stop sharing screen. So thank you very much.
Yeah, thank you, sir, for your wonderful presentation, sir. I think students have learned a lot of things about our Milky Way and black hole and other things. So we have got few questions in inbox. So if you allow, I can start our discussion session.
Yeah.
So the first question, so does dark matter form immediately after the Big Bang or later?
Sorry, does Dartmouth accept when?
So does dark matter form immediately after the Big Bang or later?
Oh, so that's a good question. So the dark matter, the actual formation of dark matter, we don't know because we don't know what it is. It's probably some kind of a particle, probably the one that was formed in the immediate aftermath of the Big Bang. It's hard to say what happens exactly in the Big Bang, but the relatively soon after the Big Bang, so in a tiny fraction of a second. And from then, it sort of, because dark matter does not experience the forces of electromagnetism and the weak force in particular, and the strong force that normal matter does, at least not strongly, dark matter would have been sort of decoupled from the rest of the matter in the universe. And so it has since been going along and forming into structures, but not necessarily, not interacting that strongly with the remaining matter. So for the purposes of the formation of black holes, there actually is an idea that some of the earliest black holes may have formed from primordial dark matter. Or even that the dark matter may be primordial black holes, which is a very interesting question, in which case its formation would be a little bit different. But generally, once the dark matter forms, it's a main component of the story, basically from there on out. And so most of what I showed you today were things that happened quite a long time after the Big Bang. And at that point, the universe has its quota of dark matter, and it's simply forming into the structures inside of which galaxies then form.
Sir, so thank you for your answer. So we have another question. So, sir, what will happen when two galaxies collide together?
What happens when galaxies collide? Great question. Let me see. I may have here a fun simulation of that I could show you. But the short answer is that when galaxies collide with each other, they have a yes, here it is. Here, actually, mind if I share screen? I can actually answer that question with a movie.
Okay, sir, you need to share.
Yep. Okay, just a second. Sharing screen. Share screen. Here we go. Share. Voila. Okay, great. So when galaxies collide with each other, what happens is their gravitational forces, they experience what they call tidal forces that strongly disrupt them. So this is a simulation of two galaxies colliding. And then this is a real Hubble Space Telescope image of two galaxies that we see. So this process, by the way, takes a billion years or so, a long time. And so we only ever see individual galaxies in the intermediate stages. But if you go and look at various places in the universe, you can actually see galaxies doing this stuff. And so what happens ultimately is the galaxies get strongly disrupted. Some of the stars are ejected, and also all of the gas in the systems get strongly disrupted. And you end up, if you have two spiral galaxies, the orbits of the stars get all mixed up, and you will end up producing with something that's more like an elliptical galaxy. And indeed, that's one of the leading ideas for how an elliptical galaxy forms is through the mergers of more disk-dominated galaxies. So this is sort of this whole lifespan showing snapshots of real galaxies in various different parts of it that happens over about 1 billion years. From the point of view of the black holes, though, I'll show you one other quick fun video. This is another simulation. This is similar, but this now shows the gas in the galaxies. So what I showed you before were the stars. This is the gas in between the stars. And what happens here, the stars, are small and don't get affected by the black hole very much. But here you have growing black holes in these galaxies. And as we talked about, the radiation from those can strongly influence the gas and can actually blow stuff out. So as these two galaxies, you can immediately see these black holes are accreting now because material had been driven down towards the center. They're releasing radiation. And as they get in close, they'll start to glow very brightly, release a ton of radiation, and boom, it can blow almost all of the gas out of this system. And so galaxy mergers may be one of at the end stage of a galaxy merger, may actually cause a galaxy to stop forming stars. Excuse me, I'll stop sharing now. Because it'll cause so much accretion onto the black hole that it'll ultimately blow out all of the remaining gas. So it's strongly related to that.
Okay, thank you, sir. We have got a similar question. So, what is the latest information available to the scientific community regarding dark matter and dark energy?
Yeah, so this is a great question. Dark matter and dark energy is the subject of a large amount of study. In a lot of ways, those are the biggest mysteries in astrophysics. The sort of thing I work on is more sort of assuming that they exist and then asking what are the kind of things that happen inside of those structures. But of course, what they actually are is a major open question. So the dark matter, we still don't really know what it is. We think it may be some kind of elementary particle, and there have actually been a number of different observations trying to look for a couple of things. One is how dark matter may actually interact with material on the Earth. So people build these big detectors and look for evidence of those interactions. We can also, people have searched for evidence of dark matter actually decaying or interacting with some other kind of particles in space. And so what you can do is observe, you say, a large galaxy cluster that we know has a lot of dark matter in it, and try to see some signatures, or for example, emission lines in the X-rays or the gamma ray part of the spectrum that would correspond to some part of that interaction. And so far, nobody's really found anything. So we don't know. So the dark matter is still very much a mystery, and it's a very much an open question. As for dark energy, it's a kind of a similar thing. We don't know what dark energy is. Dark energy is the force in the universe, you can think about it, that causes the universe's expansion to accelerate. And we don't know what it is. You can write it down in an equation. You can say what its properties are, and you can say basically what that would do to the expansion of the universe. And we're getting very significantly better measurements of that. So I showed you the lensing of the cosmic microwave background and how that can tell us how big structures are in the universe. There's a number of new surveys of the sky that are designed specifically for looking at how matter is clustered in space and how light is actually lensed by that clustered matter. So there are things like the dark energy survey, or upcoming we have the Nancy Grace Roman Space Telescope and the Vera Rubin Observatory, the LSST. Those are all designed to look at the growth of structure very accurately over the history of the universe and try to place a strong constraint on how this acceleration force, as it were, in the universe changes over time. And right now, everything is kind of consistent with it being not that interesting. It's just the simplest, it's just an extra term in Einstein's equations that you can write down as a cosmological constant. That some of you may be familiar with. So we don't know. I think everyone is hoping that what we'll learn is something more complicated than that. And indeed, one really cool thing that's happened recently is that people have found that if you measure the expansion of the universe right around us, and then you measure the expansion in the nearby universe, and then you measure the expansion rate by looking at the very distant universe, say with the cosmic microwave background, those numbers don't agree with each other. And so that may imply something kind of interesting about dark energy, but we don't know yet. And so that's still a, we're hopefully have a lot more information once these new surveys are working.
Yeah, thank you, sir. So we have another question. So can black hole be a candidate of dark matter?
Yes, they can. And so the idea basically is that dark matter in the very early universe, you can have overdensities of particles that collapse under their gravity and form into what are called primordial black holes. And those primordial black holes could, in principle, make up the dark matter if they had the right concentration and the right mass. And so there's been a number of efforts to both think about this theoretically and also predict what you would expect to see. And so far, there have been no observational constraints that have really been able to nail this down one way or the other. But this is motivating a lot of work, particularly at trying to study the early universe, as to whether we can place constraints on whether these primordial black holes exist. So it may very well be, we're in the Milky Way, where there's dark matter around us all the time. It may very well be there are lots of these small black holes all over the place, and we just don't even know about it. But that hopefully will be something that we can tighten the box on a lot better over the next decade or two.
Yeah, thank you, sir. We have another question. So, so do black hole and galaxy grow together?
Yeah, I mean, so that's in my field. That's kind of the million-dollar question. The answer seems to be, based on some of the stuff that our group has done, and I showed one example of this, that on average they do. But if you look at any individual given time, it's quite a random process. So if you look at a galaxy over the whole history of the universe, yeah, that galaxy's black hole probably grew at about a rate that was on average about the rate at which it formed stars. But it's quite variable, and there may be some other things that matter more so than just the rate of the formation of the stars. So there's been some really interesting work, particularly by the group at Penn State University here in the States, that have shown that maybe the galaxy's morphology has something to do with it too. That actually, if you have a bulge of stars rather than a disk, it's easier for the black hole to grow more quickly. And there are a number of reasons why that may be true. And so I think over the next, in fact, we just put in a proposal to NASA for some funding to potentially explore this. And so I won't give any of the details since it's supposed to be anonymous. But anyway, that's a really interesting question. I think that the answer is probably in general, but we don't know exactly how everything works.
Thank you, sir. So there is another question. So why does the massive black hole situated in the center of the galaxy?
Why is it in the center? Good question. The answer to that is actually friction, and something that we call dynamical friction. So if you put a big object inside of a galaxy, a big small object inside of a galaxy, and you move it around inside the stars, what will tend to happen is moving through the stars will cause that object to slow down. If something slows down, so you imagine you have a satellite in space. How do you get the satellite out of space? Well, you slow it down, and then it will, instead of being in orbit, it will fall in towards the Earth. So likewise, as a black hole slows down, it falls in towards the center of the gravitational potential. And that friction process will ultimately, as you have a growing galaxy with a big black hole in there, that will cause the black hole to migrate to the center and ultimately will be left there. However, this is a really interesting question because We don't know precisely how long it takes for the black hole to get all the way down to the middle. And in fact, in some scenarios, you would expect the black hole not to quite make it to the center. Once you run out of stars in the middle, there's no more of this that force that can be happening. And so you might expect some black holes to be sort of stuck in an orbit. Or they may actually be stuck in an orbit with another black hole, because if another black hole comes in, then they may orbit each other. And so we don't really know about that. But there's a real exciting possibility. You may have heard about the discovery of two black holes merging via gravitational waves with the LIGO observatory. Those were small black holes, tens of times the mass of the sun. But with the LISA observatory, which is a space-based version of that hopefully will be launched in the next decade, we would actually be able to see two big black holes merging around each other. And so that's a very exciting prospect for the next 15 or 20 years. And I'm really, really excited to see what we find there. That'll sort of answer that question definitively.
Yeah, thank you, sir. There is a similar question. So we found in comments. So when two black holes merge, does the mass of the two simply added up, or some mass is ejected?
Great question. That depends on so mostly the mass just adds up. So when you have two black holes that merge together, mostly you get a black hole with a mass that's just the sum of those two, but not exactly. And actually, this is something that has been confirmed in great detail with the observations of the two black holes. Or now we've had several observations of black holes merging together. Because we know that when black holes merge together, they produce these gravitational waves. And gravitational waves carry energy. Einstein told us that E equals mc squared. So if there's energy, that's equivalent to mass. So for when the black holes merge together, for them to be able to release that energy, that basically is taken ultimately from the masses of the black holes. And so the final black hole has a mass that's a little bit smaller than the masses of those two black holes that were merging in together. And exactly how much gets lost depends on the details of the merger. So it depends on, for example, how the black holes are spinning relative to each other when they come in. And so, yeah, it's a complicated thing. You can look up a lot of stuff about how they modeled the LIGO event and see the details of that. But so it's mostly twice the mass, but not quite.
Yeah, thank you, sir, for your wonderful presentation and nice discussion session, sir. I think students have learned a lot of things about the supermassive black hole and the growth of the galaxy. So as the main aim of our program is to motivate our students, I think you have motivated lots of our students, and I think in near future some of our students may feel interest in this field. So thanks again for accepting our invitation and giving us opportunity to attend such an important webinar, sir. So,
my pleasure.
Yeah, it's our honor, sir, to host you in our International Physics webinar, sir.
That's my pleasure, and I hope if anyone is obviously we have a wonderful scientist from Bangladesh, and we have many scientists from all over the world in our group. If anybody's ever interested in potentially coming to study or do research here at Dartmouth, you can look me up on the info right now, so please feel free to be in touch.
Yeah, of course, that will be very great for us students. So bye for today, and hope we'll arrange another webinar or face-to-face session after the COVID.
Yes, absolutely. That sounds great.
Yeah. Bye for today, sir. Good night. Have a nice day.
Thanks. Stay well.